Dear student, our next class. In the last class, we discussed about binary operation and define a field, which is an important part of this. Today's lectures, we introduce the vector space. So, before introducing the vector space, I have to define what is a vectors means. So, we start with the vectors in a plane. Vectors in a plane is simply we can say that we have a working in a plane, we have a x axis and y axis, and that is origin is there. Then there is a line segment from original to the terminal point is this. We have a, suppose we have a is a point of x1 and x2. So, this means we can say that is a this is origin, this is the initial point, and this is called, we can say that is a terminal, and this is we have to get a is initial point. So, if we have this line segment, this is we have to just say that this you have a x1, this is you have a x2. So, vectors in a plane means we have a line segment from origin to the this point. We can say that geometrically we can say that vector in a plane is represented by a directed line segment with its initial point at the origin and its terminal point at x1, x2, and this point we can just say into this form. So, we can say that, for example, if we say that we have to represent the any vector u and then we have this we represent a vector into the plane, means we have to working on a xy plane. For example, we have a x1 is equal to 2, so you have a 1, we have a 2, and y is equal to you have a 1, 2, 3, that means we have a, and then we have a, so that is a point we have a, this is a point we have a 2, 4. So, we draw as a line segment from origin to this, that means this represent as a vector in the form of a, this is a 2, 4 point is lies into this plane. So, that means this is a u is represented by this line segment. So, this line segment is represented by the u, and this is clearly this is from origin to the point to this. This is we can say that simply this is you have a up to this here is equal to 4. So, this is a 4 and this sorry, this is equal to 2 and this is you have a 4 is this. So, x is equal to you have a 2, y is equal to you have a in the 4 in this form representing this one. Now, how to add a we have to just say that add a two vectors. So, on basic vector operation is a vector addition. So, this means we can add two vectors in the plane, add their corresponding component, that is sum of a uv when u1 v2 u1 u2 and v1 v2 is represented in this form. And if you say if you go to the geometrically, we can say that this is, suppose we have a vector is equal to this is vector v, and this is vector v means this is component is equal to you have a v1 v2, and then we have a some vector is equal to you have a this is equal to u, this is the component is a u1 and u2. We have to draw a parallelogram from this, and then this is diagonal of this parallelogram. This is nothing but is equal to is u plus v. In geometrically we can say that this is nothing but is equal to u1 plus v1 and u2 plus v2, and this is the component of this thing. So, in this case we can say that in this form we have to define is a this parallelogram. So, geometrically addition of a two vectors can be represented by the parallelogram, and then we have to geometrically the sum of a two vectors in a plane can be represented by the diagonal of the parallelogram having u and v are the is adjacent vectors. We have to like this is the vector v, this is we have to taking the vector u, and then u1 u2, then we have to just say that this point to this we have to this is equal to v2, and then you have a u2, and then you have a u1 and u2. So, this means we have a this is v1, and then we have a up to this is equal to v2, and then you have a this is up to we have a u up to here we have to just go into the here this point is equal to u2, and then this is equal to you have a this element into u2. So, we have to define in this form this parallelogram by this is show that the sum of two vectors can represent in this form. That means, if we take find the sum of these two vectors, so we can just show that we know that u plus v is nothing but is equal to, if you have a u1 u2 plus v1 v2, by the definition we know that u1 plus v1 u2 plus v2. So, that means is equal to, you have a this. So, u plus here we have a u plus v can be represented in the form of this is equal to, you have a 2 5 plus 3 7. This can be written as a 2 plus 3 5 plus 7. So, this is equal to, you have a 5 and then you have a 12. So, we can say that this means simply we can say that we can add by component wise. This is the first component as adding the first one of the other vectors, similarly the second component for the second component of this. Similarly, for this we have a this vector u plus v in this case, second case we have to write in the form of a 3 and minus 5 plus minus 3 and 5 can be written as a 3 plus minus 3 plus this is 3, then we have a minus 5 plus 5 and the sum is equal to 0 and 0. So, this means the sum of these two vectors is nothing but is equal to, you have a 0 0 vector is there, and similarly we can adding this u plus v is nothing but is equal to is giving you a v itself, because u is equal to 0. So, in this case third case u plus v is equal to, you have a 0 0 1 and 4 can be written as a 0 plus 1 and 0 plus 4, and this should be 1 and 4. So, in this case we can find for example we can means simply we can say that addition of two vectors can be by adding by the component wise. Now, we have to another operation is called is a scalar multiplication. Now, we have to study the multiplication of a vector, means we have to take a two elements multiplied by this any set multiplied to is called is a multiplication, but here we have to scalar multiplication means we have to take multiplied by some scalar, and the scalar is nothing but is equal to, we have to some scalars any alpha is from to the any element of the field, real numbers or complex number or rational number, whatever field we have to this, accordingly this is the we have a. So, vector operation, another very important vector operation is a scalar multiplication. To multiply a vector v by a scalar means multiply each of the component of a v by alpha, that alpha v can be written in the form of a alpha times v1 and alpha times v2. Alpha is called as a scalar, that means and v1 v2 are the vectors is there. So, geometrically if we can say that we have a vector, say here this is you have a vector is equal to v, then we have to some multiplied by scalar. So, this means is giving you a alpha times of a v2 alpha, this is v2, then upon this is complete here to alpha v1, and this is you have a alpha times of a v2, then we can say that in this case we have to define this one. So, this means we have to write into this simply we very simple example. If we take a if we calculate if a u is equal to you have a 2 and 4 and you have a alpha is equal to we have a 1 by 2, then 1 by 2 u is equal to you have a 1 by 2 2 comma 4 is equal to you have a 1 by 2 into 2, and then you have a 1 by 2 into 4 and then is equal to 1 comma 2. So, 1 by 2 comma u is equal to you have a 1 by 1 comma 2 are the this in the form of this thing. So, this is simply we have some examples. If u is the vector of this, v is the vector of this, we have two operation addition and multiplication. This simply is we have to multiply it 1 by 3, v is equal to you have a 1 by 3 times 3 and minus 7, this is equal to 1 by 3 into 3 minus 7 1 by 3, and then we have a minus 7. So, this is equal to you have a 1 by 3 upon 3 is equal to 1, and this is equal to minus 7 by 3 is this value into a in this form. Similarly, if we calculating into this form, so we have a this first we calculating this operation 1 by 2 u, and this 1 by 2 u is equal to 1 by 2 2 comma 5, that is equal to, you have a 1 by 2 into 2, and then you have a 1 by 2 into 5, this is equal to, you have a 1 comma 5 by 2, and then we have a adding this with the u plus v. Then we have a, because 1 by 2 u we have to calculating 1 by 2 u. So 1 by 2 u is equal to, we have a 1 comma 5 by 2, then plus we have a v is equal to 3 minus 7. So this is equal to 1 plus 3, 5 by 2 minus 7, and that means this is a calculation of a 1 by 2 plus u in this case. So this is the vectors of scalar multiplications, and in addition we have to operation this. Now how to, we have to extend this definition for in place of a 2 tuples to n tuples. So we can say that if n is a positive integer, then an order n tuple is a sequence of n real numbers u1, u2, un. The set of all n tuples is called is a n space, and it is denoted by r to the power n. Because of this we have a total elements of this is equal to n. So we can say that in this case we have all n tuples are there. For example, if we take n is equal to 1, so we have a simply, if n is equal to 1, so we have a r1 is nothing but is equal to, we can say that is a set of a real number, is a only real numbers is there. Set of all real numbers is denoted by r, and r1 is a simply is equal to r is there. If we take n is equal to 2, so we have a r2, that means we have a the element of a u1 and u2, there is a 2 tuples, so that means is equal to 2 space, we can say that is equal to, is called is a space. 1 space is called is a 2 space. If we take r is equal to 3, that means is equal to u1, u2, u3, this called is a 3 space. And in the similar fashion, if we have a in place of this n elements are there, this is called is a n space is there. So this means we can simply, this is a set of n tuples, all ordered n tuples of a real numbers is denoted by the r n space. Similarly, in the similar fashion, we can define for a c to the power n, for as a set of sequence of n complex numbers where v1, v2, vn are the this thing, and then we have to share that is a n complex spaces. This is called is a n is a real space, and is called is a n is a, if we take the elements from the C, is a complex space is there. For example, if we take a 2 comma minus 1 where ordered pairs are there, there is a 2, the real 2 spaces, and this is equal to real 3 spaces, and then this is a real this we have a take elements of, this is the element of a complex numbers. So that means we have a complex 4 vectors are there. So this means you can say that is a complex 4 vectors. So it means 4 spaces are there. In the similar fashion, we can just say that. Now we have to say that when we say that 2 vectors are equal, so if u is equal to u1, u2, un, and v is equal to v1, v2, vn are 2n vectors, when we say that u is equal to v only when the equal components are the same. This means u1 is equal to u1, v1 are the same, u2 and v2 are the same, and so on, and then u and vn are the same. So if u1 is equal to u2, v1, u2 is equal to v2, and so on, un is equal to vn. In other words, we can say that the 2 vectors are equal when only when they have the ith components for all, same ith components for all I is there. So if we, for example, if we have a 2 vectors u is equal to, you have a u1, u2, u3, v is equal to, we have a suppose we have a u is equal to, we take a concrete example like this, we have a v is equal to, we have a 2, 3, and v is also, you have a 2, 3, that means these two are equal, then only in this case we can say that these 2 vectors are equal only if we have a same component. It means u1 is equal to v1, u2 is equal to v2, and so on in this form. u1 is equal to, we have this, so this means and this means u1 u2, these two are only equal if u1 is equal to -1, u3, this means u1 is equal to this, u2 is equal to this, u3 is equal to this, and u4 is equal to 8. So this means we can, by the definition, this u1, u2, u3, u4 is equal only in the case when u1 is equal to -1, u2 is equal to 3, u3 is equal to 7, u4 is equal to 8, because of the this. So that means if we take this, if and only if this equal, then we can say that these two are vectors are equal. In this case is this. Now we have to vector addition and scalar multiplication on a r to the power n. So we have to take any vectors up to Rn, and we have to take u is equal to because we have to working in the Rn, so u1, u2 up to un, v is the element of a v1, v2 up to vn. Then we have to take a u plus v two vectors, sum is equal to, you have a u1, u2 and un plus v1, v2 up to vn. Then by the sum of vectors definition, we can write u1 plus v1, u2 plus v2, and so on. We have a, you can say that this is equal to un plus vn. So we have to just say that in this form. So addition of a two vectors is defined into this form, and scalar, suppose alpha is any real number and u is element of this form, then alpha times of a u can be written as alpha times of a u1, u2 up to un. Now scalar multiplication previously we defined by the component wise, so alpha times u1, alpha times u2, alpha times un. So addition, this is called is the vector addition, and this is called is the vector scalar multiplication. So we can add any two vectors and to nth Rn space, and then we have to scalar multiplication is this thing. So this way we can define the addition, and this way we can define the scalar multiplications of these vectors into the Rn. Now what is the we come to the what is the zero vector, because zero vector in Rn. So if we have if we take a zero vector in R2, first we can take. So R2 means R2 is a two spaces there. So in R2 the elements of u is the element of a u1 and u2, and the zero vector of this is equal to, you have a nothing but is equal to is a 0 and 0. So zero vector is a vector which all components are 0, denoted by this. So zero vector is nothing but is equal to, we can 0, 0 and so on, 0, this is equal to n time. So this means r to the power n. So zero vector means simply we can say that which all components are 0 and denoted by this, and then for n vectors we have to write this is form is this thing. Example, R2 is equal to, we have a zero vector is a, or two components, both the two components are 0. R3 is equal to, we have a all three components 0, and n is equal to, we have to just say previously we can say that all n components of this is equal to 0. Now next important condition is how to subtract a subtraction of a vectors. So if you have a u is equal to, you have a u1, u2 up to un vector, v is equal to, you have a v1, v2 up to vn vector, then we have to write u minus v. This can be written as a we can write this u minus v can be written as a u plus minus v, and then we have to calculate minus v. Minus v means we have a, we can write as a minus 1 into v, and this can be written in the form of a, we have to minus multiplied each and every vector of this is equal to minus v1 minus v2 and so on minus vn. Then we have to u minus v is equal to, you have a u1 in this form, we can write in the form of it here. This is equal to u is equal to, you have a u1, u2 up to un, and then plus minus v1 minus v2 and so on minus vn, and this can be written in the form of a u1 plus minus v1 and then u2 plus minus v2, and we have a un plus minus vn. So subtraction of any two vectors can be represented into a this form. We have to write as a u1 u2 un. First we have to multiply it by this v vectors into the u, and then we have to write into this form. So now we well equipped for the define our topics of a vector space. So we define a vector space. Vector space comprise four things that together. One is very important thing is a field of scalar, which is this course is either the real number or the complex number, and we have a set V objects, and that's called as a vectors. We have an operation of vector addition that take any pair of vectors u v belongs to v and assign to them a vector v denoted by u plus v, their sum. An operation of scalar multiplication that take any scalar alpha is the element of a field and any vector u belongs to the v and assign to them a vector in a v and denoted by alpha u. So now we have to really equipped, and then we have to define the vector space, because we have four things there. I just said that vectors, field, addition, and scalar multiplication. So we have objects, we have a field, operation addition, and operation scalar multiplications we have to define for a vector space. So we have to just take a non-empty set V over a field F together with the two operations, namely one is a vector addition. Vector addition is defined in the form of a V cross V to V, where the scalar multiplication is from F cross V to V. Element of this we have to take a u v, and this is nothing but is equal to u plus v, and this is nothing but is equal to some scalar, and then you have a element of this is equal to some v, and this is mapped to alpha into v in this form, and this set v to over the field f together with these two binary operations, addition and multiplication, is said to be a vector space, and we have to generally denote it by v over field if satisfy certain axioms. For every u v w we take a element of a v, and this is known as the vectors, and then we take a alpha beta are the scalars known as the scalars or the element of field is satisfy the certain properties. First thing is should be under addition should be a closed. So we have a this under addition we have to define from v cross v to v. That means we have a u and v are the element of a v. Then we have to u plus v. So first one thing should be take a for any we have to take a for any u and v are the element of a v. Then we have to show that then this implies that u plus v is also the element of a v, means this should be a closed under addition. So we should be a closed under addition. Then we have already u, v, and w are the element of a v. So we have to take a u plus v plus w is equal to same as a u plus v plus w. For all we have a for all uv belongs to w, that means associativity under commutative law or associative law for a vector addition is satisfied. Also commutative law for vector addition is also satisfied. So we have a v plus u is the same as a v plus w, and v plus this associativity is there. Now we have a there exists an element 0. We have a say that there exists an element v denoted by 0, such that find element such that 0 will add to the any element of this vectors giving the vector itself, and this is called as the existence of identity, additive identity, or we can say the existence of identity, or we can say simply say the existence of additive identity is there. Now, the last under addition, we have a condition is this: for each u in V, there exists an element minus u in V such that u plus minus u is equal to 0. This condition is called the existence of a additive inverse. So, if vectors, these two binary operations satisfy under addition these properties, close under vector addition, under addition is commutative, under addition is associative, additive identity should be exist, and additive inverse is there. So under addition now we have to also satisfy under scalar multiplications. So under scalar multiplication means we have to define from field V2 we have a V, that means we have a alpha is then is a scalar, then V, and this is alpha V types elements are there. So first is for any u belongs to u, then scalar alpha u should be element of a V, means we can say that this closed under the scalar multiplication. And also distributive law for scalars, we can take a two scalars alpha and beta, alpha plus beta over the vector, then we can satisfy this one condition. Also satisfy the another distributive law, alpha and sum of vectors satisfy this alpha u plus alpha v, distributive law for vectors, and also satisfy the distributive associative law for scalars multiplications. So we have a alpha times beta u is equal to alpha beta u, or we can say that beta alpha u in this form satisfy this condition. And the last one, if it is satisfied that 1 u into is equal to u is there. So if this we can say this vector space V over a field F under addition and scalar multiplication satisfies all these axioms so then this set V is called as a vector space. Now we take a field of this, so this is a vector space over a field. So this means in this course we have a field, either field is a real number or field is either is a complex number. If we take a field is a real number, so field is a real number, we already proved is a field. If f is equal to r, the real field, then vector space is called is a real vector space. And if take a field as a complex number, then V is called as a complex vector space. So that means we can say simply that if we have a field of reals, then vector space is called as a real vector space. If field is a complex, then vector space is a complex vector space. Now we to try to vector space over a different types of a field. Suppose we just say that we take a set vector V is a set of a complex number, and then we take a V as a set of a complex number, and we have to take a field as a real number. Then you just say that this is addition. So we take a any two element U and V are the element of a C. Then you know that if you take a sum of a two complex number is again is a complex number, that means this is closed under the addition. If alpha is the element of a field is a R, so alpha is from R and U is the element of a complex number, then alpha U is again is belongs to the complex number. So that means this is again is a closed under the scalar multiplications. Also in the complex number, you know that 0 plus I0 is the element. This is the element of a C, and U is the element of U tested at A plus IB. If we take a of 0 is equal to A plus IB plus 0 plus IB, this is equal to A plus 0 plus I times sorry A plus I, sorry, this is you have I times 0. So this is we can say that V plus 0, and this is nothing but is equal to A plus IB is equal to U. So this means element is there, inverse identity element is there. So this is the additive identity in this case. And also we have to take a, if U can be written as a plus IB is the element of a C, then minus U can be written as a minus A plus we have a I times minus B is the element of a C. Then if you take a u plus minus u, this is nothing but is equal to a plus ib plus minus a plus I times minus b. This can be written as a minus a plus I times b minus b. A and b are the any real number. So this is equal to 0 plus I times of 0, and this is nothing but is equal to 0. So this means every element, this we have to say that it satisfies the conditions of a inverse also there. And because the complex number is associative and commutative, so we can say that u plus v can be satisfy v plus u, and u plus v plus w also satisfy this form. And we have to, because we have to alpha plus beta times u, this can be also satisfy alpha plus beta. So alpha plus beta times you have a b, a plus ib. Alpha times beta is some real number. This is also the element of a c. We can write alpha a plus beta a by the associative distributive property of a real number. So it satisfies all the properties of a vector space. Then we can say that it satisfies all the properties of vector space. Means clearly this is it's a complex number, is a vector space of this. Is R over Z? This means we can take a V is equal to, we have to taking as a R, and we have to F is equal to, we have to taking a SC. So is this is a this we take a U and V are the element of a V, then U plus V are the element of a V, because is V is a real number. So sum of a two real numbers is again is a real number. Now alpha is the element of a C, and then we have a U is the element of a V, V is equal to, you have a R. So this means if we take a I times, we take a any element of a R, so we take a, suppose alpha is equal to, we take a 1 plus I, and U is equal to, we take a 2, then this is equal to 1 plus I into 2. This is not the element of a real number. Is clearly, this means this is a not closed under the scalar. This implies that alpha into u does not belongs to the R, means this is set is not a closed over the addition scalar multiplication. So this set is not form a vector space over the this thing. So this is clearly no. Now, if R over vector space is clearly no problem, V is equal to, you have a set of real number, and F is equal to, you have a K. Yes, this is a clearly is the same. Sum of a two real number is again real number, and some rational number over a scalar is a rational, and real, this is a real, and then it also belongs to the real number. So it is closed, and this clearly this we can find a vector space, satisfy all other properties of this vector space. Is Q is a vector space over R? No, because why not? Alpha is the R and U is the this. The alpha U is, does not imply it belongs to the Q. So root 2 is the element of R, then root 2 into 1, this is clearly not belongs to the Q. So this means we can say that this root 2 into 1 is not. So this means clearly this set is not a is closed under the scalar multiplication. So this is not again is a this again not a vector space of this thing. So now I think I have to stop here this lecture, and in next class we have to discuss some examples of a vector spaces. So thank you very much for the next class.